Hello everyone, I'm Jonathan Parlett, and this is going to be a third in a series of videos to go over some C fundamentals for CS260. So today we're going to go over a dynamic array. We're going to create a dynamic data structure. So to motivate this, let's talk about Python lists. So Python lists are a familiar data structure. It should be to everyone here. They can store an arbitrary amount of elements and even store elements of different types in the same list. So the important thing here is an arbitrary number of elements that they can store. So knowing what you know about memory, how do you think they store so many elements? It would be very inefficient to simply allocate space for a billion items and just hope no one goes over the limit. So that's probably not what they do. What they actually do is grow in size as items are added to them. So the underlying data structure of a Python list is actually just an array. That's what it uses under the hood. The size of this array is what is adjusted as items are added. So using what we covered so far, we're going to create something like this. We're going to create a dynamic array data structure. It's going to grow in size automatically as we store elements in it. We'll use a pointer to store our data on the heap, and we'll adjust the amount of memory allocated to this program or allocated to this pointer in our program as the array goes in size. So things to keep in mind as we're writing this code. Try to relate what we're doing to the concepts we've previously discussed, such as dynamic versus static memory. As we write, try to notice where in the program we're using dynamic versus static. Spoiler, this is going to be all dynamic pretty much. As we write, try to think about what information we're storing on the heap and what we're storing on the stack. A lot of it's going to be the stack whenever we're doing pointers and things like that. Remember, information is on the stack. The memory model. If a structure is confusing, try to use the model we showed previously. The model of memory as a table, just a bunch of cells with data in them, and indices are addresses. So everyone has their own style of writing code and thinking about problems. This is just mine. You don't have to do things exactly as I do them. So that out of the way, let's get started. So first, let's just create a code folder for this. Array, C. And then let's open that up in VS Code and send that to workspace 4 and code folder. Okay, so the first thing we need is a structure, the basic structure of our array, right? We're going to do this with the familiar idiom type destruct. What are we going to call this? We're just going to call it a list, just like it is in Python. So again, the underlying data structure of a Python list is just an array. So we're going to do the same thing. But maybe let's abstract this out and think about it a little more generally. So one, we need a place to store things. So where we store stuff. Two, we probably want to track the size. So the number of elements currently in our list. Three, so we're increasing the capacity of our list as we add elements to it to make sure it's dynamic. We can continually grow it. So we'll probably want to store this capacity. So the max number of elements in our list, or max number of elements we can store in our list, to be very accurate. So we're just going to make this list function just for the integer data type, not anything else. So we're going to have an int pointer, we'll call it vals. This is where we're going to store our integers, the items of our list. And then we're just going to have an integer, call it size, and an integer, call it capacity. You would probably actually want to use like the size underscore t type here if you wanted to be very safe and not worry about signed values, but we're never really going to have anything that big, and it's easier to just think about using an integer everywhere. So we're just going to do that. Okay, so we can get a list structure or a pointer to a list item by just doing list pointer L. So at this point, it's declared, but it's a pointer, right? So it has no memory allocated to it. It has no place to store anything. So if you try to do anything with it now, before you allocate anything, you would probably just get a seg fault or some weird undefined behavior. So first, you actually want to malloc memory for our structure here. Size of, just like we've done before in the previous video, when we have a type, we can just allocate size for that type. And obviously we want assignment equals, not comparison equals. So we're getting an error here because we are implicitly declaring a library function malloc. So this is just because we forgot to actually include the header file that gives us malloc. So we're going to include stdlib.h because that is where malloc lives. And now we can allocate space for our array or our dynamic array, our list. So we have to think about a few things. When we're using this structure, what do we want it to originally be able to hold? So what is the initial capacity going to be? And then we also obviously need to actually allocate enough space for that capacity number of elements, okay? So this is starting to get weird. We have a lot of stuff to do, such as, okay, allocate space for initial capacity, assign initial capacity, and we need to initialize start size to 0, because initially we're not going to store anything. Okay, well, would we really want to do this every time we want like a type, one of our list data structures? This is a data structure, right? It's like a Python list. We might want like 30 of these in a program, maybe. You wouldn't want to do this every time in like the main code block. It'd just be very messy. So it kind of feels like we need a constructor. So this is usually the first thing I always make whenever I'm making a data structure like this. It's always, you're always first going to make a constructor for it. And that constructor essentially is going to do what we were about to do here. So first, we're going to allocate space for the structure itself. So that gets us space for our int size and our int capacity. We still need to allocate space for vals, and we need to assign these initial values. So this should really be after initial capacity. So initial capacity, we'll just set it to 1. So L capacity equals 1. And then we need to allocate space for the initial capacity. And this is vals, right? So we need to allocate space for vals. So we're going to say size of int times L capacity. In this case, we know is this going to be 1, but maybe we want to change this code later. Maybe we initially want to store like 100 things because we know we'll always store at least 100 things. So it just makes it easier to update this way. And then initial start size should be 0. Initial size is empty. So now to get an instance of our list data structure, we can just say list pointer L equals list, and we just call the function. And that's it. So that's pretty nice, right? It's a convenient way to do things. And like I said, you're usually going to want to follow this kind of structure whenever you're implementing a data structure in this course. Make a constructor for it first. It should be like the first thing you do. And let's slow down and think, where are things being stored? So first, the list data structure itself is a list pointer. It's a pointer to an item of type list. So this actually is already stored on the stack. The pointer itself, remember, so what does our memory space look like for this? Let's go to explain everything. And let's draw some memory for our program. So what were we talking about again? So we'll say this is stack and this is heap down here. And we're just going to say they're separated by this line. And remember, in reality, they grow towards each other. There is no defined separation. But this actual declaration here, list pointer L, in the main function. List pointer L. This is stored on the stack up here. Okay. But the actual data, the members of this struct, so like capacity, or let's just say this is the definition. So inside this struct, we have int capacity, just call it cap, and int size. Since this was just given an address on the stack, and it was space is allocated on the heap, sorry. These are all stored on the heap. That means also that the int pointer vals, this is also stored on the heap. I think previously in our previous videos, we might have given the impression that like, oh, whenever you're declaring a pointer, it's always like the actual thing itself is stored on the stack. Not always. In this case, even just the pointer itself, the declaration in pointer vals, it itself is stored on the stack, and it will also have a stack address when we allocate space, or it itself is stored on the heap, and it itself will have a heap address as its value. Okay, cool. So let's like not forget everything we learned in the previous videos. Okay, so next we probably want to be able to add things to our list. And I also should note that we forgot something here. This has a list pointer return type. If we never return L, then we don't have any list, do we? But anyways, so we would like to be able to add things to our list. But before we do that, let's do some basic testing. So we know this should be able to store at least one thing, and it should be stored at L vals sub 0. We should be able to set this equal to say like 2 or something. And then we should be able to like print it. So let's just do that. Vals sub 0 equals %d. And we'll say L vals sub 0. And let's go ahead and run that. Okay, and we say it's equal to what we set it to. And more importantly, this initialization function worked and did not give us any seg faults. It's a really good idea to test your code incrementally as you're writing it just like this. You finish this function, test its implementation. Okay, that being said, we would not want to add elements like this every time. You would not want to index into the array to set an element, and then like what we need is functions, or in an object-oriented land, we would want methods to be able to add elements and things like that. So we're going to do just that. We're going to have an append function. So the append function probably shouldn't return anything. It doesn't need to. For arguments, it should take a list pointer L, and then the data that you're going to add to the list. So int data. Got that backwards for a second. We are not in Go. So yeah. So where are you going to append things to? You're going to put them at the end of the list. Think about the fact that size of list is 1 greater than the last index. So assuming size less than capacity, we can place an element at the index size. That might be confusing, but all I'm saying is where we always want to place something is going to be L sub vals sub L sub size. And we're going to set this equal to data. So if you don't see why this works, just think about it a little bit. Yeah. Okay, so we could use append this way, right? We can do append L2. And that works just fine. And what if we say add 2 more things and print 2 more things? we'll say this is 3, this is 5, and we're going to look at 1 and 2. Okay. Now this is indicative of one thing we forgot that we need when we're appending. You obviously want to increase size. So we'll just say L size plus plus, increase size by 1 whenever you append something. That's why this initially showed up as 0 here, because we did not add anything. We did not increase size, so it just overrode 0 every time. So R sub 1 and sub 2, just to make that accurate labeling. Okay, so there's a huge problem here though. We've only allocated space for one integer. We're getting away with writing integers into space that we haven't allocated, but eventually it's going to bite us in the ass. Pardon my language. To say, for example, yeah, let's say int I equals 0, I less than a bunch, I plus plus. And we're going to append L, I. And yeah, thank God, we have a segmentation fault, wonderful. So we're writing space further and further down, or further and further up in memory. Eventually, we probably overrode our own stack and basically shot ourselves in the foot. But eventually, we ran into another program's memory space. And this is because we're not allocating additional space, so we're not requesting additional space. So we eventually we have whatever the operating system gave us initially, and we run over it. If you don't want to think about that, then just remember that doing this is undefined behavior. Writing into memory that you have not allocated is really bad. And if you get random segmentation faults later down the line in your program, it might be because you forgot to do something like this. You made a mistake like this where you forgot to allocate more space. And it didn't initially appear to be wrong because it just let you do it, because it's not technically always going to give you a segmentation fault doing this because it's just undefined behavior, but it will eventually probably screw you over. So just be careful of this. So the correct way to do this is with this condition here. So assuming size is less than capacity. So at a certain point, size equals capacity. And this is the point where we cannot add anything else. So if L size equals L capacity, then we've maxed out. We can't add anything else. If we try to write to the sizeth place, we'll just get a segmentation fault or something else, or whatever, undefined behavior will happen. Okay, so if this happens, we want to increase our capacity, right? This is where the dynamic part comes in. So we'll say L capacity equals L capacity times 2, which this could also just be L capacity times equals 2. And to be more succinct, we'll do that. And then after we've done this, we want to resize our list. So resize L capacity. Okay. Now, obviously, resize is not a built-in function. We have to implement this. So as we were writing code, we saw that, oh, we have this problem and we need to fix it. So we're going to go back and write something else. So resize probably doesn't need to take anything. It doesn't need to return any arguments. So we will just say it returns void, and then it should take a list pointer L, right? And then a integer new size. So let's think about what we learned so far and what we need to do now. So we know how to create new dynamic arrays, pointers, or yeah, we know how to create arrays using pointers and malloc and all of that. And we know how to copy information between arrays, static or dynamic. It's the same process. This is basically all we need to do. We need to create an array that has enough space for the new size, right? And then we need to copy everything from the old array to the new one, and then deallocate the old one and remember the new one. So let's say create new vals, allocate enough space for new size num of integers. And then we want to copy from old vals to new vals. And then what we want to do, we want to free old vals because we don't want to create a segfault. And then we're going to set old vals equals new vals, which is to say we want to set the int pointer vals member to our new pointer that we've created. Okay, so let's create new vals. Well, we just do this with a normal declaration. So int pointer new vals. And then we want to allocate enough space for new size num of integers. So we'll say new vals equals malloc size of int times new size, right? We need that many integers, exactly. We need space for that many integers, exactly. That's what we've requested. So we're going to now copy from old vals to new vals. So we know the size of the dynamic array at this point. It hasn't changed. So we know we had that many elements. So we can just copy them over with a simple for loop. So for int I equals 0, I less than L, size I plus plus. And all we're going to do is set new vals sub I equal to L vals sub I. And remember, we don't want to create a memory leak. We don't need the current L vals pointer anymore. So we're just going to free it. Free L vals. And then we're going to update L vals. So L vals is now going to be equal to new vals. So yeah, this should be good. Now we can allocate, we've increased the size dynamically, we've increased the capacity. Sorry, confusing those two things. We've increased the capacity, not the size. We'll increase the size once we add a new item, which we'll do after we've resized our array. And we have, more importantly, have reclaimed the memory for the old array. We tossed it away and we've done it efficiently. So that's good. So yeah, now this actually should not crash, and it doesn't. You see, we first add 2, 3, 4, 5, or 2, 3, 5, and then we add like 10,000 things. We're only printing the first few things, so this just kind of works. Even though it has, what's that, 100,000 things in it? Yeah. So one more thing you're always going to want to do usually is make a print function for your data structure. So we're going to do void print list, which is just going to take a list pointer, L, and it's going to print its points. So for int I equals 0, I less than L size, I plus plus. And we're just going to print them in a space separated manner. So we're going to say just the integer itself. That's going to be L sub vals sub I. Okay. And then we're going to print a new line. So we can have each entry of this print. So a single print of the array is going to be on a single line, which is not going to be great for when we get larger and larger arrays, but it'll be good for what we're trying to do. Okay, so let's say after all this, let's call print list. And let's give it our list L. And this is going to be very large output. So let's go up here. Let's go into our dynamic array. And let's make our, yeah. So we can see we get all the way up to 99999. or just one under 100,000, which makes sense because we added things while starting at 0 up to, but not equal to 100,000. Okay. So it looks like our append works, our resize works, our constructor works. What else do we need to do? Well, one other thing that you always want to do for any data structure is have a delete function, or like a make null or make void. We'll just call it delete in this case because we don't really need the name for anything else. So what this is going to do is going to free the data structure that you just created. You made a constructor, you need a destructor. This should take an instance of a list pointer L, and it should say, so obviously the structure of this thing is very similar to what we looked at previously when we were instantiating and freeing a struct with an array as a member. So just like we did then, we first need to free the vals pointer before we free L itself. And then we can free L. Yeah, and we would just want to call this at the end of our program so we don't have a memory leak. Program does not really run, or it doesn't really change, but it is running. Okay. Yeah, I should mention that memory is always deallocated and freed automatically when the program ends. So this is why nothing really changes here. Memory leak isn't really very consequential in this case, because even if it's never deallocated before the program ends, all it does is just add things and then the program dies. That's it. But in a program that's going to be running for a very long time or more complicated structures, you really are going to want to have this delete function handy for when you need to, like, say, deallocate an entire linked list. But yeah, one more thing to make this like very obvious, let's print the capacity whenever we resize our array. So let's just do printf capacity %t section capacity. And then let's say not add 100,000 things, let's just add 100 things, and let's take the rest of these out. And let's print every time we add something so we can see how this really grows. Okay, and let's zoom out there. So you can see it grows in kind of this pyramid shape. The capacity is initially 2, and then capacity is initially 0 up here, and then you add the number 0. Then the capacity becomes 2, and you add the number 1, and then it doubles to 4, and you add 2 and 3, and then it doubles to 8, and then 16, 32, 64, 128. So again, you can see it increases in powers of 2 because it started as power of 2, and we're just doubling each time. But yeah. Okay. So this is a pretty well-functioning data structure. But let's see if we can make it a little more efficient. Let's think about this resize function. So again, what we're doing here, let's just reset this actually. Whenever we're doing a resize, it's pretty bad. So say this is our list. List. This is all of its items stored in memory at some location. Okay. When we are resizing it, we are finding some new location that is as big as we want it to be, and we're moving all of our items there before we just get rid of this. It would be faster if instead of copying everything every time, we could just extend the amount of space directly in front of it. Copying takes time, it's expensive. But if there's free space directly in front of where you already allocated, you can just drag that forward and it's totally fine. No one else is using that memory. That's what you would like to do. But you can't do that directly, but the operating system can do that. It can see when there is space directly in front of the pointer you already have, and it can just extend that out. And we can take advantage of this property, not ourselves, but by using a function called realloc. And it's going to make our resizing a whole lot simpler. So reading about realloc a little bit, it just takes a void pointer and a size, and it returns the void pointer. And what does it do? The realloc function changes the size of the memory block pointed to by pointer to size bytes. The contents will be unchanged in the range from the start of the region up to the minimum of the old new sizes. If new size is larger than old size, then added memory will not be initialized. If a pointer is null, the call is equivalent to malloc size. Yeah, so we can use it like this. We would say L sub vals equals realloc L sub vals L capacity. So potentially we avoid doing all of this, and instead we just extend our range of memory a little bit. And we can see that this doesn't change anything functionally. It's still the same. So do another make run. Oh, yeah. Wonderful. Yeah, this is less than the original size. What was the original size? What was the size of the int times the capacity? Not great. So what this should be is allocating enough space for capacity number of integers. So malloc, or sorry, times just size of int. So we're going to resize it to that. Okay. Now it shouldn't actually change at all. Yep. And you can still see that the capacity is increasing in the same way, doubling each time, and we still get this nice pyramid shape here as we're adding things to our list. All just with the function realloc. So obviously this is a lot simpler to use, right? But that behavior I talked about isn't going to be taken advantage of very much. In reality, what realloc is doing is what we were doing here. It's probably going to look at it and say, well, I don't have enough space in front of me. So what I'm going to do is make a new pointer. I'm going to allocate the requested amount of space for that pointer. I'm going to copy everything from the pointer you gave me to a new pointer. And then I'm going to return that new pointer and I'm going to free the old one that you gave me. So this process we did manually here, this is all realloc is going to do under the hood for the most part. But yeah. So let's think about this a little bit more theoretically. You might want to go through this code and think, where are things stored? What's stored on the stack versus the heap? For instance, we talked a little bit how because this is a pointer, everything in it is basically stored on the heap, to include things like the size and the capacity. Again, is this stored on the heap? Is the list pointer itself here stored on the heap? Is in the constructor, is this declaration stored on the heap? Where is this stored? Is it stored at all? Or is its value just returned? And you should also recognize here that we're using dynamic memory basically everywhere in this program. The only places we're really utilizing static is a few declarations and some sub-functions and in the main function, obviously. But yeah, this should be a pretty good model of what you're going to do every time you're building some data structure in this course. You're going to have a constructor, and then you're going to have the requested methods that you should implement. And you're probably going to end up making some sub functions, some helper functions to enable you to accomplish the original task that you wanted to. And then you're also going to have a function to deallocate the dynamic structure that you created. But yeah, I think that's about it for today. Thank you for your time. Have a good one.